So welcome to Module 5, Part 1. So we are making our way. We're getting through the material. After this week, we have one more week of new material. So there's 6 modules. And I know Bridget had a great question where she asked, but there's 7 deliverables. And that is correct, and I'd like to just throw it out there so everybody knows the expectations. I talked about this in the first video, but you may have forgotten since it's been like 5 weeks, right? There are 6 deliverables, each based on a module. The 7th deliverable is cumulative, but if you want to, you can actually get started on deliverable 7 now. So if you really wanted to, you could go check that out and get started, because we've learned actually all the material you'll need for that deliverable, the cumulative deliverable. So if you want to get started on that, feel free. But if you're just trying to take it week by week, that's okay as well. Do whatever you feel comfortable with, because remember, this is a 12-week class. You have 12 weeks to finish it. But if you want to get done sooner, you can. If you want to take a little bit longer, that's okay as well. So, what are we talking about this week? This week, we're going to revisit hypothesis testing, but this time we're going to use 2 samples. So this week is really good because, one, it will help break down last week a little bit more and hopefully stick it, make it a little bit more concrete, those concepts of hypothesis testing and what are we really testing for. The other thing is we're just going to expand on it a little bit more. So there's one new formula, I think. Otherwise, just a couple variables that are similar to what we learned before. So very, very similar to everything we've talked about before. So hopefully this week feels a little bit easier than last week when it was all new about the hypothesis testing. So last week, what we did is we looked at one sample. So for example, in your deliverable 4, you had the one sample of all 364 jobs, right? And all their different salaries. That was one sample that we were looking at. Well, this week, we're going to look at 2 different samples. So think of it like if I had 2 different classes and maybe I did a sample from class A and a sample from class B, and then I were comparing those 2 samples. Those would be 2 different samples. So in our deliverable this week, we will have a new problem. So hopefully that's exciting. You won't be working with the same Excel sheet you have been working with, but we'll be doing 2 samples and we'll talk about how that works. So when would we use this? So in the real world, oftentimes we like to compare and contrast. So for example, a drug company might want to test the effectiveness of a drug. And to prove something, you often have to have a control group. And for anybody kind of in the medical world, you might be more familiar with this, but control group is a group where they're not taking the drug, or they're taking a placebo, which means that it doesn't have any effect on the people. And that control group, you want to measure the differences that are happening there versus the group that's actually taking the drugs to see the difference between those 2 groups, okay? And to see how well the drug actually affects it. And this is especially true like weight loss drugs and stuff, where you've got the group that thinks they're taking the pill, but they're actually not, and you're comparing the 2. So something like that. So this doing 2 samples is very, very common. I just said that, but comparing 2 different types of weight loss drugs and 2 different groups of people, we're going to go through some examples as we go through the practice problems as well. So they'll be in there, but just know we have 2 different samples. They may be doing the same thing, they may be doing something different, and we're going to compare the results from each of those samples and see if there's a difference between the 2 groups, okay? 2 groups of things. Okay, Now, when we look at these two groups, we have to define them as either independent of one another or dependent on one another. So we're going to have to talk about that. Two samples are independent of one another if the sample values from one population are not related to or somehow naturally paired or match with the sample values from the other population. So independent means that they're not related, okay? So my class A would be independent of my class B because they aren't related. I'm just looking at taking two samples and looking at their information. You can often tell that two samples are independent if they have different sizes. That's one way to tell it. But for example, the comparing two different types of weight loss on two different groups of people. So one group giving the placebo pill and one group giving the actual pill, that would be independent because they're not relying on one another or they're not matched up. And that'll make more sense once we talk about dependent. But independent, they're not relying on one another. They're independent of each other. Now, oh, you should probably write that down. Often different sample sizes. Okay, make sure you write that down. But what I mean by that is like my class A, my class B, maybe I have in my first section of this course, I have like 183 students. In my other section, I think I have like 35. So those are different sizes. So that's kind of a dead giveaway that they're independent of one another. Because dependent samples have to be the same size, and so you can make a little note, have to be the same size. Size, I can spell. Okay. Or they're going to be matched pairs. So what does that mean? So here's an example. A group of subjects, group of people, were put on a weight loss drug. And then that same group of people were taken off of the drug, and they're seen and they check to see what their weight loss progress was after, to see if the drug had an effect or not. So what's happening here is it's dependent because it's the same group of people. You're just taking away the drug, okay? So you're matching to see, okay, person A on the drug, how'd they do? Person A off the drug, how did they do? What was the difference between the two? And you do that for all the people on the drug. So it's like you're matching up those people, okay? So dependent, you can match them up. It's sort of like, it's a dead giveaway if they're the same size. In other words, they have to be the same size. Independent can be the same size, but they don't have to be. Okay. Oh, I have the hint right there. If two samples have different sample size, it's automatically independent. If they have the same size, you have to look at it a little bit closer to tell if it's independent or dependent. So we're looking at two samples, two populations, okay? Two samples, two populations. So we're going to give them new variables, but don't be scared because these variables are very familiar. Why are they very familiar? They're just the variables we know with either 1 or 2 in the lower right-hand corner. So let's look at population 1. Population 1 is going to have a mean 1, that's our mu1 would be how you would call that, mu1. And it just is referring to the population mean of population 1. Whereas population 2 is mu2. So the population mean in group 2. Population standard deviation, again, the population standard deviation is that variable sigma. But Depending on the population, it'll either be population 1 or 2. Same thing, population proportion. Proportion from 1, proportion from 2. I know we didn't talk about proportion very much. We're not going to get into it a whole lot. That's just like the percentage. So if like 90% of the students are done with deliverable 2 in my first class and 88% of my students are done with deliverable 1 in my second class, those would be the proportions of class 1 or class 2. So P1 and P2. So sample size, N1 refers to the sample size in the first group, in the first sample, whereas N2 would be the sample size in the second one. So that would be like I have 83 students in my first class, so that would be N1. N2 would be the 36 students I have in my second class. So the two different group sizes. Now the two samples can match. Okay, the two sample sizes can be the same. For dependent groups, they definitely have to be the same because you actually have to match them up, which we'll get to in tomorrow's example. Okay, sample mean. Now this looks kind of funny to me, but that's supposed to be X bar. It looks really weird right now, but that's supposed to be X bar sub 1, X bar 2. X bar 1, X bar 2. So just the sample mean from the first group, the average of that first group, and then X bar 2 would be the average of the second group. Sample standard deviation is S, S1, S2, group 1 or group 2. And then sample proportion is P hat 1 and P hat 2. So just the proportion from group 1 and the proportion of group 2 for each sample. Any questions on these variables that you want to ask? So hopefully these all look familiar. We've talked about them several times. Some may be more familiar than others. Keep in mind, if you haven't done so already, I did mention this to quite a few students, so I just thought I'd share it real quick. If you haven't done so, please make sure in the live lecture notes that you download the symbols guide, and it might be a good idea to actually print that symbols guide out to help you if you're struggling with identifying those variables, because it's so important to be able to quickly identify which variables are which, okay? So if you haven't done that, check that out as well. Okay, so let's keep going. So we are actually going to work this first part by doing independent samples. The rest of this video is about independent samples. Tomorrow we're going to come back and see how it differs for dependent samples. So for independent samples, we're going to talk about looking at the two samples and try to infer about their two means. So we're going to concentrate on the population mean, okay, and trying to draw a conclusion about the mean. So note, we are going to approach the problems as if sigma 1 and sigma 2 are unknown. So remember last week we talked about this concept. If we don't know the population standard deviation, which is sigma, we use our t-test statistic. We're going to roll that over to this week as well. We don't know our population standard deviation. We may know the sample, S, but we don't know sigma. We're going to use the t again. So that was the difference. So we're going to use that t again. Is everybody with me so far? Sounding very familiar? Hopefully. Okay. Now this is where things change and get a little dicier, but we can handle it. We can do it. Yes, we can. Okay. To calculate the t statistic when you have two samples, you have to use this formula. Do not freak out yet, okay? You out there, no, don't freak out, okay? I'm going to show you how to break it down. You know I do. I got your back. Hint, it has to do with plugging this into Excel and being very careful about parentheses. I already got like 3 or 4 emails this weekend about parentheses. So as I was saying last week, parentheses are very, very important. So please remember your parentheses. Very, very important. Okay. So T equals. Okay. So what you're going to do is you're going to take your sample means from group 1 and group 2, and you're going to subtract them on the top. Okay. Now over here we have our population means that we're subtracting. Well, we are going to assume for our null hypothesis that the sample means are the same. So if you subtract the same number, you actually get 0. So it's almost like we're subtracting 0. So when we type in our T statistic into Excel, we're really just going to take X bar of 1 and subtract X bar 2. Okay, so we're just going to take and subtract the sample means because this part right here actually falls away. It's 0. We don't need to worry about that. So instead, we're just going to subtract our 2 sample means in the numerator. In the denominator, what we're going to do is we're going to take the square root of our sample standard deviation in group 1 squared divided by the sample size in group 1, add it to the sample standard deviation in group 2 squared, and divide it by n2. That can get a little confusing, so we're going to walk through that a couple times on how to plug it in Excel and make sure you're being clear. So we definitely want to use those cell references to be clear and help clean up any of the mess that might be there. Okay? Now, degrees of freedom is going to be a little bit different. The last 4, we only talked about degrees of freedom for the last 2 weeks. For the last 2 weeks, when we talked about degrees of freedom, we took the sample size and we subtracted 1, correct? Well, now that there's 2 groups which might have a different sample, like the 183 students and 36 students, we need to do something a little bit different because they don't have the same sample size. What we need to do instead is we need to pick whichever value is smaller. So basically what you're going to do is you're going to pick the smaller sample size, whichever one is smaller, so in our case it would be the 36, and subtract 1. That'll be your degrees of freedom. Always choose the smaller sample size and subtract 1. Okay? Okay. Now the good news, I have good news. We will be not downloading the new iTunes update. Thank you, computer. Go away. Okay. We will be testing the hypothesis using the same steps as before. Yay! Woo, woo, woo! So all that time and energy you spent last week learning those steps, it is worth it, and you're going to use it again today. Okay. So, and again, you can either choose the critical value or the p-test to test it out. The only thing that's different is the test statistic formula. It's the only thing different, okay? Oh, actually, I lied. The whole null hypothesis and the alternative hypothesis will look slightly different. And that's just because what we're testing. So we're comparing these 2 samples. So the null hypothesis is that there's no difference between the 2 samples, okay? That the average, the mu, is the same. So our null hypothesis is still equal, but we're not going to put a number in there. Instead, we're going to say, okay, well, my null hypothesis is there's no difference between these 2 groups, meaning that their mu's are equal. So mu1 is equal to mu2. So it's still equal for the null hypothesis. The alternative still has that option of not equal to, less than, or greater than. So that's very similar to last week, okay? The only difference here is that you have either the two mu's are not equal, mu1 is less than mu2, or mu1 is greater than mu2. So here we're saying, let's look at the two groups and let's compare them with one another. So maybe the average in the first group is smaller. We would put a less than. Maybe the average of group 1 is larger. Then we would put a greater than. So really the same idea as we worked with last week. The main difference in the null and alternative hypothesis is instead of numbers, we are actually just going to be comparing the two mu's. I actually think this is easier because you don't even have to pick out a number. You're just putting the two mu's up there and then just figuring out what inequality goes between. So maybe, okay, we'll see. Okay, so I know you're ready to knock out an example. So this is from the book. A book. I don't know if it's your book or not, but anyways, basically, I got this from the book, and what they did is they weighed a bunch of cans of Diet Coke, and they got the following results for Diet Coke. N is equal to 36, so they weighed 36 cans. Sample size was 36. That should read X bar. So if it doesn't read X bar on your sheet, please change that. So X bar, the average weight was 0.78 pounds. So a little under a pound, okay? Now the sample standard deviation for the Diet Coke was 0.00439. So very, very small number. That's okay. We'll type it into Excel. It'll take care of it, okay? Now that was the first group, Diet Coke, okay? The second group was regular Coke. So there are two different groups. So the idea is they're both independent of one another. They actually have the same sample size, but that's just a coincidence. We could have taken a different sample size. It wouldn't have mattered because they're independent of one another, basically because they're not matched. Okay, it's not like can 1 has to match with can 1 in the other group or anything like that. So Diet Coke and regular Coke, two different groups. And in the regular Coke, we took 36 cans. Our X bar, our average weight was 0.81 pounds. And our sample standard deviation was 0.007, so a little bit more variation for the Coke. Now they want us to use a 0.05 significance level to test the claim that the contents of cans of Diet Coke have weights with a mean less than the mean for regular Coke. So you know what I'm going to do? Same thing I did last week. Let's highlight the claim. I like to highlight that claim. Doesn't hurt. So I know what we're doing. Yay! Okay. And then I'm going to make sure I underline Diet Coke has a mean that is less than regular Coke. So that's going to come back and be important when we come up with our alternative hypothesis. So step 1 through 3 is to create the null hypothesis and the alternative hypothesis. So again, we start with mu1 and mu2. Now in the null hypothesis, what symbol do I put between these mu's? Equals. Yes, it's always equal. Not a trick question, just equals. Yeah, very good. Now in the alternative, we're going to make Diet Coke group 1 and we're going to make regular Coke group 2. So here when we compare the mean of group 1, which is Diet Coke, and the mean of group 2, what is our claim? What are we testing here? The HA is going to be what we're going to test. So what symbol is going to go between the means? What do you think? Less than, yeah. Oh, I didn't see you over there. Yep, you're absolutely right. It is less than. Because Diet Coke, which is group 1, should be less than regular Coke, which is group 2. So that's how we set it up. Very similar to last week. Now, step 4, because 1 through 3 is all done. Step 4, we need to figure out our significance level, which is actually given. I just covered it up. It's 0.05. It's our favorite, 0.05. Okay. Now, before I move on, I just want to point out real quickly that the same rules apply from last week as this week. The alternative hypothesis determines if it's left-tailed, right-tailed, or two-tailed. So what do you guys think? Is this left-tailed, right-tailed, or two-tailed? What do we think? Left, right, or two? Yes, it is left-tailed. So I'm going to put a little note here that says left-tailed because it's less than. And that will help us when we get to the critical value, but it's good to just note that as we're moving along so that when we come back to it, remember, oh, it's less than, it's left-tailed. And remember, we're still going to be using those worksheets. So claim uses a less than, it's left-tailed. So these worksheets that I gave you last week still apply. So good news, using a lot of stuff from last week, right? Okay. Now, oops. Okay. So now what we need to do is calculate the test statistic. Now this is going to be a little bit trickier, but we can do it. Test statistic. So we're trying to come up with our t-value. Now just as a reminder, it's x bar sub 1 minus x bar sub 2 divided by the square root of s sub 1 squared divided by n sub 1 minus s sub 2 squared over n sub 2. So we definitely want to label these. So since Diet Coke is group 1, I'm going to label this N1, X bar 1, and S1. Since regular Coke is going to be my second group, I'm just going to label it N2, X bar 2, and S2. And then I'm going to go ahead and type this into Excel. So I want to make sure I've got all my information here. So what I'm going to do is I'm going to go N1 is 36, X bar 1 is 0.78479. Don't want to round it. S1 is 0.00439. I wish there was a nicer way to type these into Excel, but I have not really found that. That's okay. And then what I'm going to do is something a little bit different. I'm going to jump over so I can write N2 so I don't confuse the two. 36 X bar 2 is 0.81682. And S2 is 0.00751. Okay. So just going to double check I got those in all correctly. So what I'm going to do is jump out down here and you type in my test statistic. Boop. Okay. Now in here, equals, the top goes in parentheses. So I'm going to choose X bar 1. So notice X bar 1 is up here. I just use my cell reference, and this is going to make it really nice and clean. So I'm going to select B3. That's where I have my X bar 1. Hit the subtract, and then choose X bar 2. So it's subtracting the two means. I'm going to divide it by the square root. So SQRT parentheses. Now, so we're taking the square root of everything in there. This can get a little tricky. So we need another set of No, we don't. We're fine. Okay. So we actually don't need another set of parentheses. Instead, what we're going to do is we're going to choose S sub 1, this number right here. We're going to square it. So this is the Shift 6 button. Shift 6 gives you an up arrow. That indicates an exponent. So you're multiplying it by itself. Then we're going to divide by N1. So I'm going to grab N1 up here. Hit subtract. So here I am in the formula. So all we did was we typed in this first part. Okay. Now we need to subtract and type in the second part. So S sub 2 squared. So I'm going to grab S sub 2. Again, I'm going to square it by hitting Shift 6, 2. That's going to square that number. I'm going to divide it by N2. N2 is our sample size of group 2, which is 36. Okay. After I type that all in, take your time on that. If we rush through things, we're more likely to make an error. So go ahead, take your time when you're doing that. Close the parenthesis. So it's going to say take the square root of everything on the bottom. Okay. I'm just leaving this open for a second in case anybody needs to write it down. Hit enter. And I did something wrong. I mean, you could, but it'd be overkill. The only reason you would is if you want to do parentheses around the square root. You could do that. No. There's something not right. Oh, why did this happen? Subtract. You don't need parentheses there. What if I do throw parentheses? Did this last time, it worked just fine. Let's see if that works. Why are you yelling at me? I didn't type in something correctly. B3 minus E3. Square root. Okay, I'm just going to delete this and start over because sometimes that's just the best thing to do. Okay. You can put those in parentheses, but you shouldn't have to. Let's try it just for good. Okay, well, it just yelled at me. Hold on, sorry guys. S2 squared divided by... I did this before. I don't know why it's yelling at me. Wonderful. So that's awesome sauce. No, because you're missing the back half. Hold on. Oh, it's plus. So this is awesome. It's supposed to be plus. That's why, because you're getting a negative underneath the square root. Oh my goodness. Okay, so this is why we say, always review the formula, even if you think you know it 100%. So that's embarrassing. It's a plus. There we go. That was exciting. Okay, let me go ahead and pull it up. So everything was right. This has to be a plus. Otherwise, you're going to get a negative underneath the square root, which you can't take a negative because that's an imaginary number, and we aren't dealing with imaginaries right now. So any questions on that? Literally, it was just me messing up the minus to a plus. That's lovely. Boop. Answer would be negative 22. Negative 22.09. Yep. Now on the PowerPoint, I abbreviate, or I round it. Okay, negative 22.09. I round the answer, but when you're doing further calculations, use the number that's in your worksheet. Don't use the rounded number. I didn't clarify that before, so I want to make sure I clarify it now. Okay, well that was super fun and everything. Let's go ahead and move on and test our statistic to see if we should reject the null hypothesis or do not reject the null hypothesis. Those are our two options, right? So there are two ways to do it. We could do the critical value, and then there's the P method, which one do you guys like? Which one do you guys like more? Anybody? Oh, the plus sign was right here in the square root. So it should not be a subtraction, it should be a plus. You like the critical value method more? Yeah, it's one of those things where it's like some people like one or some people like the other. Yeah. Okay, so the critical value, since it is left-tailed, boop, we're going to use that, and we're going to go to our worksheet for left-tailed. We're going to say, okay, critical value, what do you tell me to do for left-tailed? Well, I need to use T dot inverse of alpha, comma, degrees of freedom. So let's go ahead and do that. So critical value is T dot inverse of alpha, comma, degrees of freedom. So alpha is going to be 0.05 because that's our alpha. That's what's defined. Now our degrees of freedom, remember you're picking the smaller sample size. They're both the same here, so pick one sample size and subtract 1. So what's our degrees of freedom? A 35. Yes. 36 minus 1 is just 35. Okay, let's plug that in, see what we get. What is our critical value? Make some room down here. So critical value. You can make a song to it, that's okay. T dot inverse. Now this time it's going to actually work and not make me really angry at Excel. Okay, so it looks like our critical value is laughable. It's negative 1.69. You could round that up to 9. Is that what everybody got? Negative 1.69? Yes? Okay. Okay, so our critical value, negative 1.69. Now, what does that mean? So if you remember, we have our beautiful t distribution that looks like our normal distribution, zeros in the middle. Our critical value determines where the rejection region is. So our critical value, CV, is at negative 1.69. This tells us that the rejection region starts there. So if our test statistic falls into that rejection region, we reject the null hypothesis. If it doesn't, we say, yay, we do not reject the null hypothesis. So, do we reject our null hypothesis? Bridget says, yes, we need to reject it, and that is correct because our test statistic is negative 22. So if you were to draw this number line, woo, way over here, our test statistic would literally be way over here. So it would definitely reject. Okay, it's way over in the rejection region. So in other words, since our test statistic is less than our critical value, we reject the null hypothesis, which is HO. So negative 22.09 is less than negative 1.69. I mean, the test statistic is so negative, it's laughable. It's a huge laughable number. Like, it's clearly rejected. There's no question about that. So we reject the null hypothesis, okay? But we want to do the p-value method to double check that we did it correctly. So the p-value method, we take the test statistic and we do t.dis to find the probability of that test statistic. So it is t, comma, degrees of freedom, comma, true. Since it's a left-tailed, I'm sorry, I should go into that for a second to show you guys. So again, p-values, to find your p-value, you're going to this worksheet, left-tailed, and they tell us t-dot distribution, test statistic, degrees of freedom, true. So all of our instructions are on here if you ever get confused on that one. Okay. So let's go ahead and plug in our t distribution, which is negative 22.09. Our degrees of freedom, which we stated over here, was n-1, which is 35. And true because it's always true. That one never changes. It's one thing that never changes we can be happy about. It's always true on the end there. Okay, so we want to do our p-value. So t.dist. Now I'm going to use, I'm not going to type in negative 22.09. I'm going to use my cell reference to grab that test statistic. And then comma, our degrees of freedom, tells me what to plug in there. Cumulative, I'm always going to type in true. It's always true. So t.dist, I've got my test statistic first, got my degrees of freedom second, and true. We hit enter. Now, this number says 1.93376e to the negative 22. We've seen this before, but I want to review this a little bit. When you have an e in there, that means it is in scientific notation. And when it's in scientific notation with a negative exponent, it's saying the exponent is negative 22. That means there are literally, imagine 22 zeros, actually it's 21 zeros before 1. So 0.0000000000000, 22 zeros, 19376. It's a very small number. Like, you need a microscope to see that number. It's so tiny. So basically you have an itty bitty number here. Okay. And to write that down, you would write it like this. So your p-value is equal to 1.93 times 10 to the negative 22. Basically, it's saying it's a really, 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 really small number. There's basically 22 zeros before 1.193. Blah, 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 blah. And Dan, you're absolutely right. You could go ahead and expand that cell really, really wide, but you have to expand it really, really, really wide. There's not enough room on the screen for that, right? Yeah, exactly, Dan. You got it. Okay, so when we're doing p-value, that's good. When we're doing p-value, we need to compare it to our alpha, kind of like that really dorky picture I posted in the course. I don't know if you guys checked it out. Did you guys check out my really dorky picture? Okay. So Grandma always said to reject the null hypothesis when your p-value is less than your alpha. Okay. So she's always told you that. She's always told you that. Okay. So what does that mean? My p-value, since it's really, really tiny, my p-value is less than my alpha. Since 1.93 times 10 to the negative 22 zeros, is definitely less than 0.05, which only has 1 zero in that decimal place. This one has 22 zeros after the decimal. Actually, 21 zeros after the decimal. So if it's less than alpha, we reject the null hypothesis. So we are going to reject the null hypothesis. Yay, they match. Yay, life is complete. Isn't that wonderful? Yay. Okay. You guys are clearly very, very, very excited. Can't believe it. Life's amazing. Okay, so is there sufficient evidence or not? We can always go back. So the last thing we need to do is come up with our conclusion. So, let's go back here. Okay, it is a less than. So when we reject the null, evidence supports claim. So what do we say here? Let's throw up a little something, something. So we can support the claim. There is sufficient evidence to support the claim that and I ran out of room, so I'm just going to highlight what you should be writing. That the contents of cans of Diet Coke have weights with a mean that is less than the mean for regular Coke. Somehow, Diet Coke, even though it has the same volume, weighs less than regular Coke. Interesting. No? Just me? Okay, great. I'm just going to give you guys a second. So question, guys. Does this feel very similar to last week? Are you digging this because you're like, okay, we did something like it last week. That feels good. The only thing that's different is how you set up the null and alternative and then the test statistic. And the test statistic obviously was a little kooky, but that's okay. Okay, hopefully I gave everybody enough time to write down that claim. Let's go ahead and do one more example. So basically the University of British Columbia conducted trials to investigate the effects of color on creativity. Does color affect creativity? Interesting. Subjects with a red background were asked to think of creative uses for a brick. So basically a brick with a red background. Come up with some ideas on what you would do with brick. Other subjects were given a blue background and were given the same task. So this kind of like plays into psychology and seeing how it affects it. Interesting. Responses were scored by a panel of judges and results from scores of creativity are given below. So how creative are you with this book? Higher scores correspond to more creativity. The researchers make the claim that blue enhances performance on a creative task. Okay, so they're saying if you see blue, you're more creative. Okay, interesting. Now, use a 0.01 significance level to test the claim. So different level of significance to test the claim that blue enhances performance on a creative task. Now, when they were looking at these two groups, these two are independent groups because it's not the same group that did it twice, right? Okay, it's not the same group. One looked at a red background, one looked at a blue, because obviously that wouldn't work because they already know what the task is, so that doesn't help. Instead, they're two different groups. They're actually two different group sizes, if you notice there. One's 35, one's 36. That's a dead giveaway that they're independent because you can't match them up. So one looked at red, one looked at blue. Here's all the information. Let's go ahead and call the first group, group 1. So we're going to label all their variables 1. Group 2, we're just going to label all their variables 2. First step is to come up with your null hypothesis and your alternative hypothesis. So our null hypothesis always starts out the same. What do we throw in our null hypothesis? It's my favorite part. Equals, yes. Now, again, we're going to do the alternative. So I'm going to label red group 1 and blue group 2. Let's come back to the claim. So I like to highlight a claim. The claim is that blue enhances performance on a creative task. So we have to be careful here though. So the idea is that which one should be larger, red or blue? Which creative should be larger, red or blue? So their claim is that blue enhances performance. So blue should be greater. Does that make sense? Blue enhances, so blue should be greater. Blue should be a larger creative number. That's okay. I want to make sure I'm just being clear. So if blue is creative and blue should be larger, so blue is larger number. That means since blue is group 2 should be larger. So the inequality should be eating group 2. So, yep, mu1 is actually less than mu2. So here we're reading it as the red is smaller than the blue. So just be careful, and on the homework you won't have this problem, but just be careful you're identifying the appropriate groups. So it really helps to label them to help lay that out. Okay? Okay, so quick question, is this left-tailed, right-tailed, two-tailed? What do we think? Left-tailed, right-tailed, two-tailed. It is left-tailed. I'm going to write that down here real quick. Left-tailed. Simply because it is less than. If it was greater than, it would be right-tailed. So just as a reminder. And if we had flipped the two groups, like if we had labeled blue group, group 1, and red group, group 2, our method would look different, but we'd come up with the same conclusion whether or not to reject the null or do not reject the null. So still come up with the same conclusion, just have to do it a different way. So just be careful about what you label. Okay, so what is my alpha? My alpha is actually different. It says 0.01. The significance level is alpha, just as a reminder. Okay, great. Now let's go ahead and calculate the test statistic because I kind of screwed that up on the last example, so we need to make sure we go through that. Boop. So t equals x bar sub 1 minus x bar sub 2 all over square root. There's a plus sign between them. We learned that today. Let's see. S sub 1 squared over n sub 1. S sub 2 squared over n sub 2. Okay, so let's go ahead. I'm just going to use that same Excel sheet. I'm just going to delete all my information and just type in my new information. So Bridget, we aren't there yet, but we always use the smaller n value to calculate the degrees of freedom. Yeah. So you might be there. So I'm assuming that's why you asked, and that's totally cool. Okay, so 35, 3.39, and 0.97, all the information for group 1. I just wrote it vertical instead of horizontal. So group 1 is this way. I just typed it in. Group 2, I'm just going to type in boop. Okay. Gotcha. Yeah. So give that right. Okay, so test statistic, parentheses around the top. We're going to grab x bar 1. We're going to subtract x bar sub 2. We're going to divide by the square root. Parentheses, now we type in the bottom. So I'm going to grab s sub 1, 0.97. Shift 6 gives me the up arrow, so I'm squaring that sample standard deviation, dividing it by n sub 1. Now we add, I'm still bitter about that. I'm not going to forget that. Okay, s sub 2 squared, and divide that by n2. Okay, close parentheses. Okay, so we've got our numerator, our x bars, our sample means being subtracted, square root, squaring our sample standard deviation, dividing it by the sample size, adding that to our other bit. Hit enter. Okay, we do have a more reasonable number this time. We have negative 2.98. I'm going to round that. Negative 2.98 is our test statistic. So, hey, that's not too bad. We'll have to see how that plays out. Negative 2.98. Let me pull up the assignment again. N1 is underneath S1 squared. So it's right here. Got it? Okay. So now that we have our test statistic, now we go ahead and we determine either using the p-value or the critical value. Boop. Okay. I'm going to do this a little different this time. I'm just going to write it at a different way. So let's do the critical value first. Apparently we're using Christmas values. Critical value. I don't know why. Okay, now this is a left-tailed, so we're going to use that same method, t dot inverse. Alpha, comma, degrees of freedom. Alpha is 0.01, so it's a little bit different this time. And our degrees of freedom, I mentioned this earlier, but let me reiterate that. Degrees of freedom are n minus 1. The n that you pick is the smaller of the two. So what n should we be using here to find the degrees of freedom? going to use the smaller n, which is 35. 35 minus 1 is 34. So that's what we'll be using to plug into Excel to come up with our critical value that determines our rejection region. Okay, I was very excited about that today. T dot inverse. 0.01 is our alpha. Degrees of freedom are 34. Hit enter. Negative 2.44. So this one's actually a close one. This one's pretty close. See how that works out there. Negative 2.44. So here is our wonderful curve. We've got 0 in the middle. Now our rejection region is on the left. It's negative 2.44 is our rejection region, our critical value. So that's where our rejection region starts. Okay, and the question is, does our test statistic fall in the rejection region? What do you guys think? Is negative 2.98 going to be smaller or larger? It's a little bit smaller. Negative 2.98 is a little bit smaller. So our test statistic is less than our critical value, meaning we do reject our null hypothesis. Oh my gosh. Okay. I need to get a grip, people. So rejecting our null hypothesis. Yay. So what should we expect in our p-value? P-value. We should reject. Yes. Okay, so again, same thing. Let's do some t-dot distribution. It's a less than, so we're going to do the same thing we did on the last problem. We've got our test statistic, test stat. We've got our degrees of freedom, and we've got true. That's true. I know it looks like nothing, but it's true. Okay, so test statistic is negative 2.98. We are going to use the value in our Excel cell reference. And degrees of freedom is 34 because you're always picking which sample? The smaller one. Okay, let's plug that in. Let's see what we get. What do we get for our p-value? Anybody? Anybody? Anybody do that yet? T-dot dist. And I'm going to select my test statistic. Degrees of freedom are 34 and true. Boop. It does look like we got the same thing, Bridget. It is 0.00265. I don't even need to go that far, but that's okay. Okay, so let's talk about our p-value because it's a little bit different this time. This time we really do need to look at that. Our p-value is 0.002. We can round that up to 7. That's okay. So what we're doing is we're comparing this p-value to our alpha. Now be careful because our alpha is different. It's 0.01 this time. So we're looking at that 99% confidence. 0.01. So which one is larger? So make sure you compare by decimal points. So the first, the 10th position, they both have 0. Okay, neither one is bigger. The 100th position, which is the second decimal, notice the 1 is actually larger. So in fact, the alpha is actually larger. And that one can be a common mistake because you look and you see 2 and you're like, oh, 2's bigger. But the 2 is actually in the third place, the thousandths place. So it's smaller. So you want to be careful. Just go each decimal place and compare. So That would mean alpha is larger, p-value is less than. So if p-value is less than alpha, we reject. That's why it's always good to take your time and really analyze those problems. But then we get into the whole problem of like overanalyzing. Yeah, it's hard to find that happy medium, and the only way we find our happy medium is with more practice, unfortunately. So that's kind of what happens. So if your p-value is small, the hose got to go. Remember that from last week? That's terrible. That's terrible. Okay. So the last thing I want to leave you with is our conclusion, which is if we reject the hoe, yeah, it's the same situation. There is not sufficient, or there is sufficient, excuse me, there is sufficient evidence to support the claim that and because of time, I'm just going to say that blue enhances performance on a creative task. So in fact, there is sufficient evidence. Okay, so I'm not going to go over the last one here, but it's very similar. Let me go ahead and just pull up the homework so we can look at it. This week, again, we are on deliverable 5. Now, this week you're a statistician working for a drug company. Yes, they make a lot of money. It's pretty good. Okay. A few new scientists have been hired by your company. They're experts in pharmacology, but are not experts in doing statistical studies. So you have to explain to them how statistical studies are done when testing 2 samples for the effectiveness of a drug. Basically, you just have to do a hypothesis test and explain what you do. So, there is just a Word document. There's no Excel document given. However, notice the rest of it. All calculations should be provided on a separate Excel workbook and have to be submitted along with the Word document. So even though they don't give you an Excel document, you need to make sure all your work is done on the Excel document. Okay? I want to make sure I'm clear on that. Okay, so this is your assignment. You're only really able to do the first 3 parts of this. The second part is for a dependent sample, which we haven't talked about yet. We will talk about that tomorrow. So for independent samples, basically, one of your researchers wishes to determine whether people with high blood pressure can reduce their blood pressure by taking a new drug. Okay, they want to test this. The sample data is shown below, where X bar 1 represents the mean blood pressure of the treatment group, so who's taking the drug, and X bar 2 represents the mean for the control group. So those are the people that are taking the placebo that don't know it, okay? And we're using a significance level of 0.01 and the critical value method to test the claim that the drug, which is the treatment group, reduces the blood pressure. We do not know the values of the population standard deviation, only the sample that are given. Okay? So this is the information. These first 2 columns are for the treatment group, which are the group that are getting the drug, okay, that are taking the drug. The second part here is the control group, and they are just getting the placebo. They're not actually getting the drug. So you can see N2 is 70, X bar 2 is 201, and S2 is 39.8. So number 1, write the hypotheses, in symbolic form. HO, HA. Determine if the test is right-tailed, left-tailed, or two-tailed, and explain why. We talked about that, and we talked about it last week, so hopefully that feels good. Number 1 feels good. Number 2, calculate the critical value and the test statistic. You don't have to do it in that order. You just have to show how you would calculate the test statistic and how you would calculate the critical value. Now in this one, you're actually only doing the critical value method. You're not doing the p-value. So you're going to do the critical value in 2. And then in step 3, you're going to make a decision based on the critical value you just found about the null hypothesis. Do we reject it? Do we not reject it? And then explain your reasoning just based on critical value and the test statistic, and make a conclusion about the claim in non-technical terms. So there is sufficient evidence, there is not sufficient evidence. So you can get through 3 today. Tomorrow we'll talk about dependent samples. It's a little bit different. It's going to be working through a lot of the ideas we talked about last week, but you are going to have to calculate a couple things that are new. So definitely wait until tomorrow to touch on that one, okay? Any questions on the first homework? Hopefully you're feeling better, a little bit better this week. If you do have questions, feel free to reach out to me. Otherwise, I hope that first part goes well. So Dan asked, is there a better cheat sheet with symbol definition, long formula, and Excel formula function? Not that I'm aware of. That's the worksheet that we came up with. Honestly, for you guys, I would say if you want a worksheet that has like your formulas too, I'd almost say just write them out on like a worksheet so that you have that as a reference, because I don't have anything like that. I'm sorry. So yeah, this one, it's just so that you guys can grab the symbols. And then you can see the first column is sample, the second one is population. And you can just grab it to use. Oh, you tried to look it up, Dan, and you're like, no. Yeah, I wouldn't even dare looking through Google and try to Google a list of all the formulas, because a lot of statistics classes don't use Excel. They force you to do it by hand, which I'm glad we don't. But so they probably do it differently, and they don't have Excel on there. So sorry about that. Maybe I'll think about how to do a sheet at the end or something for summary. I'll look into what I want to add on there, but that's a good idea, Dan. Thank you. Any other questions or suggestions or thoughts? Always happy to hear ideas. Yep, Lestina, yep. Symbolic form is just the hypothesis, just writing the hypothesis in symbol form. So HO, HA, and then whatever it is. Yeah. Any other questions? And if you need to, if you don't want to write it out, like H, let's see if I can write this real quick. Like H, okay, come on. Nope, nope. HO, you can just write H, and then there's a subscript button. You can just hit the subscript to hit O, and then click it again to get out of there if you want to. That's another way to write it out there. Yeah. There's little tricks that you can find. Okay, all great suggestions. So I appreciate everybody coming tonight. And hopefully I will see you tomorrow to talk about dependent samples, and hopefully I'll hear about how the first 3 problems went. Okay, I will talk to you all later. Have a great rest of the night. Bye, everyone. Bye, Bridget. Bye, Dan. Bye, Dan. Listina. Bye.